Welcome! Now I'm going to talk about basis and dimension. In a vector space, one can talk about linear independence. So let V be a vector space. A set of vectors, B, is said to be linearly independent if any finite linear combination, sum I equals 1 to n alpha I, some coefficient alpha I, times bi, equaling the zero vector with b1 to bn taken from b, is only possible if all the coefficients vanish. So this implies alpha 1 equals alpha n equals 0. The next concept is spanning system. A set of vectors S in V is a spanning system for V, or spans V, if any vector of V can be written as a linear combination of finitely many elements of this spanning system. X equals sum I equals 1 to n alpha I si and si to sn are in this spanning system. And the third concept is basis. The set B of vectors in the vector space is a basis for V if first B is linearly independent, and second, if B spans the vector space V, or B is a spanning system for V. An important mathematical result is the basis theorem. Any vector space has a basis. And even more, all bases of a given vector space have the same cardinality. And if the cardinality of a basis is finite, you see a basis can be also an infinite set of vectors. But if a basis has finite cardinality, this is then the dimension of the vector space V. Testing linear independence. Given vectors a1 to an in V, you may ask, are these vectors linearly independent? Okay, so set a linear combination alpha 1 a1 plus and so on plus n an equal to zero vector, and find out if the only solution for this equation consists in all alpha being 0. So if V is r to the n, then we obtain a homogeneous linear system of equations, which we can just write as ax equals 0. So you're asking for the solution space of this linear system of equations, a equals 0, and linear independence is given if and only if the solution is unique. a1 to an is linearly independent if and only if ax equals 0 has a unique solution. The theory of systems of linear equations then says that this unique solution is the trivial solution, all entries of this solution vector 0, all coefficients alpha equal to 0. An issue about dimension. If U is a subspace of a vector space V, then we can compare the dimensions. Namely, dimension of U is at most the dimension of V. The reason is that you can take any basis of U and then extend it to a basis of V. This is the basis extension theorem. And that's why the basis count here cannot be larger than the basis count here. Example, take these vectors 2, 1, 1, 1, and 7, 5 in R2. Are these vectors linearly independent? The answer is given just by counting. So what's the dimension of this space? It is 2. And how many vectors do we have here? 3. So any subspace of R2 which they span can have dimension at most 2. That means these 3 vectors are linearly dependent. And thank you very much.